Good morning. Today we are going to discuss about Beryl class of hexagonal system. This class is quite different from the other systems because hexagonal system possesses four axes, whereas the rest of the crystal system possesses three axes. So basically, due to the presence of four axes, the characteristic of this class is fairly different from the other classes. As we have already studied about the isometric system, tetragonal system, then we went for orthorhombic system. In that, we have observed that the symmetry was gradually decreasing because in isometric system to orthorhombic system, the axial pattern got more and more asymmetric. But there is a sudden increase in the symmetry of the hexagonal system because of the higher symmetry in the axial system because of the presence of four axes. So let us discuss about the hexagonal system. So as I told, the hexagonal system consists of four axes. Out of four, three are horizontal axis, whereas the fourth one is vertical axis. In the diagram, you can see how the axis of hexagonal system are arranged. You can see here that each horizontal axis is separated by 120 degree with the subsequent horizontal axis. These three axes, which are horizontal, are equal in length, and hence they are named as A1, A2, and A3. And they are separated by 120 degree angle. But the third axis, which is vertical to these three axes, is different in length. It could be either longer or shorter. In that case, this is named differently, that is C. Because as we know that the nomenclature has to be done on the basis of equality and inequality. So if the three horizontal axes are equal in length, hence they can be named as A1, A2, and A3, whereas the third one can be named as C as it is different from the rest of the axes. The three horizontal axes are separated by the angle of 120 degree, whereas the third vertical axis is perpendicular to all these three axes. The front end of the A1 will be referred as positive end, whereas the rear end will be referred as negative end. In the diagram, you can see where the A2 is written. You have to measure 120 degree and then consider that axis as A2, and the right end will be the positive and the left end will be the negative. Then again, you have to measure 120 degree from the A2. Then the axis which will encounter will be A3. Then that end will be uh, positive, whereas the reverse end will be negative. So it is slightly complex uh, in hexagonal system to to assign the positive and negative ends. The third axis is the C axis, where the top end is the positive and the bottom end is the negative. So this is the actual diagram of the hexagonal system. Let us see the symmetry elements. As I have already discussed that the uh, symmetry of the hexagonal system is quite higher when you compare it with the tetragonal and the orthorhombic system, because there are four axes and out of them three axes are equal in length, and because of which there is a slight increase in the symmetry in comparison to the tetragonal system. But the hexagonal system cannot achieve the symmetry of the isometric system. So in isometric system, there were 9, 13, 13, 9, and 1. In tetragonal, there were 5, 5, and 1. In orthorhombic, there were 3, 3, and 1. But in hexagonal, you get 7, 7, and 1. So there are 7 axes of symmetry, 7 plane of symmetry, and 1 center of symmetry. Now you have to see in the 7 axes of symmetry, there are 6 axes of different nature and 1 axis of different nature. Okay, so the one axis which is vertical is of six-fold symmetry, and the remaining 6 axes which are along the horizontal plane are of two-fold symmetry. So it is very clear that if you will hold the crystal along the vertical axis and if you rotate the crystal, there will be the repetition of phase. There will be a repetition, there will be a 6 times repetition of the referred phase. But if you will hold the crystal along the two-fold axis, then there has to be the repetition of the repetition for 2 times along that axis. So the referred phase will repeat itself twice if you will hold the crystal along the two-fold symmetry axis, whereas if you hold the crystal along the six-fold symmetry axis, the referred phase will repeat itself for 6 times. So these 7 axes of symmetries are classified simply in the six-fold axis, in the six-fold axis of symmetry and the two-fold axis of symmetry. So you can see in the diagram that the vertical axis, the hexagon is mentioned there. It indicates the six-fold symmetry, whereas the red one, the red marking is for the two-fold symmetry. Now let us see the 7 plane of symmetries. Here, out of 7, the 6 planes are vertical in nature, whereas the 1 plane is horizontal in nature. The vertical plane will divide the crystal into 2 equal halves. So there are 6 such vertical planes, whereas there is 1 horizontal plane along which if you cut the crystal, you will get the 2 equal halves. And of course, the third picture will indicate the center of symmetry. As usual, this system has such a great geometry or symmetry. So it is but obvious to have a center of symmetry over there. So now you can see that you can depict the symmetry elements of the hexagonal system where 7 axes, 7 plane and 1 center of symmetry is there. In 7 axes, 1 hexagonal or 1 six-fold symmetry, or the six are two-fold symmetries. In 7 plane of symmetries, we have 6 vertical planes and 1 horizontal plane, and there is 1 center of symmetry. Now we'll move towards the forms of the hexagonal system. So the forms of the hexagonal system are very complex as compared to the isometric system. Okay, you can see here we have prism in the tetragonal system as well. We have prism in the tetragonal system as well as in the hexagonal system. Here you can see these prisms are quite different from the tetragonal system. You can see here the prism of first order and the prism of second order. The prism of first order and prism of second order are same, only the orientation of axis is different, and because of which their notations are quite different. You can see here in first order of prism, the notation, the Miller indice is 1 0 bar 1 0. It is the first order prism. But the moment you rotate the axis within, the rotation will become 1 1 bar 2 0. Okay, so you can see here in the first order, the axes are intercepting at the edge of the face. But in the second order of prism, the axis is not intercepting at the edge, but it is intercepting at the face. And because of which the notation is the notation has changed. So in first order it was 1 0 bar 1 0. It is a representative notation, whereas in the second order prism, the representative notation is 1 1 bar 2 0. It is like complex. Okay, you have to read it, you have to understand it. If you don't get it, you can just put your query, no problem. The third well-known form is dihexagonal prism. So if there are 6 faces in the prism, then of course in the dihexagonal prism there will be 12 faces, and accordingly the notation will change. 2 1 bar 3 0 is the representative notation for the dihexagonal prism. And you must remember that the prism is an open form. Okay, so it only consists of 6 or 12 faces. When you will close that open form by the 2 faces, from top and from below, those 2 faces are known as pinacoids. Okay, and there are 4 numbers in the Miller indices. As we have seen that in isometric tetragonal orthonomic there were only 3 numbers because there were 3 axes. But in hexagonal system there are 4 axes, and because of which you have to indicate the notation by 4 digits. The next well-known form is the bipyramid. You can see here, it is just advanced form of octahedron. It is also known as bipyramids. And also in orthorhombic system also we have seen the bipyramids. And in hexagonal system there are bipyramids. They're also having first order and second order bipyramids. These forms are a little complex if you compare them with the isometric and the tetragonal or orthorhombic system. Now let us see the examples of the isometric system, sorry, hexagonal system. The well-known examples are graphite, beryl. Here you can see the graphite crystal on the left end of your screen, whereas at the right end of your screen, you can see the crystal of beryl. These two are well-known examples of the hexagonal crystal system, whereas beryl is the normal class of the system. Okay, you can see here this beryl is indicating the hexagonal form. Okay, so let us revise the hexagonal system. So today we have discussed about the Beryl class of hexagonal system, in which we have four axes. Out of them, three are horizontal and one is vertical. Three axes are equal in length and hence named as A1, A2, and A3. They are separated by 120-degree angle. The fourth axis is vertical and perpendicular to these axes, whereas the fourth axis is different in length, hence the name C. The symmetry elements are slight higher than tetragonal and orthorhombic. We have 7 axes of symmetry. Out of them, one is hexagonal. Six are one is of six-fold symmetry, whereas six are two-fold symmetry. Then we have 7 plane symmetry, in which six are vertical planes. One is horizontal plane. Then we have one center of symmetry. Then we have well-known forms like the prism of first order, represented by 1 0 bar 1 0. Prism of second order, represented by 1 1 bar 2 0. This first and second order depends upon the orientation of axis. The dihexagonal prism, the bipyramid, and the pinacoids are there. The well-known examples are graphite and beryl. So thank you very much for your attention. Thank you very much.